to give this presentation. Okay, so there will be two parts. The first one will discuss the fundamental electrochemistry in fuel cells, and the second part will be more devoted to electrocatalysis and the catalyst used for a very important fuel cell reaction, namely hydrogen oxidation, CO oxidation. CO is a part of the reformable gas when you process any fuel, and oxygen reduction, which has a very bad point. Okay. So that's the outline of my presentation. I think some of these topics were discussed yesterday. Okay, I just begin with the beginning. The beginning is very hard. I need a pointer somewhere. Don't have. Okay. So at the beginning, it was the famous Grove experiment, and in fact, also Schönbein, German-Swiss scientist, was involved. Both of them published a 1 month shift in early 1839, the principle of the fuel cells. So in the hydrogen-oxygen fuel cells, as you saw yesterday, you have the reaction of hydrogen with oxygen. It is a combustion reaction, but it is made with electrochemical reaction. It means there is no fire, no explosion. It's very smooth at room temperature. But for that you need, of course, some catalyst, because this reaction, which is normally possible at room temperature, because the thermodynamic data, they are negative. So if delta G is negative, the reaction is possible, this spontaneous reaction, and if delta H is negative, you have energy from the reaction. And this reaction with the figure, you see, that's relatively large amount of energy. If you convert the energy in kilojoule per mole into kilowatts per kilo, for electrical engineers, they prefer kilowatts in kilo. So you get a very huge amount of energy, 33 kilowatts per kilo. Okay? With the transformation of chemical energy into electrical energy, the key thermodynamic quantity is Gibbs energy, variation during the reaction. So this Gibbs energy allow you to calculate the standard electromotive force under standard condition, means 25 degrees, and you get 1.3 volt. If you compare to the Leclanché cell, 1.5, or to lead acid accumulator battery, 2 volt. So that's the standard electromotive force or standard cell voltage under standard condition. And with the other part of the reaction, the data, the change of enthalpy, you can calculate a theoretical efficiency. So I say again, it is theoretical. Under standard condition, means under reversible condition, in the sense of thermodynamics. So you get 83% of efficiency, which is very high, but it is theoretical. Okay. And I also add that this reaction looks like the reverse of water electrolysis. It means if you take water, if you provide energy, because it is not spontaneous, the reverse reaction is not spontaneous. You cannot do that except if you provide external energy. Okay? So you provide electricity and you get hydrogen and oxygen. It was very important at that time because in 1801, Volta discovered as elementary cell. It's mixture of copper and zinc elementary cell. So Grove and Schönbein, they have the possibility to make electrolysis. Okay? So they tried to decompose water. They succeeded, and they got in a glass tube hydrogen and oxygen by decomposing water in a sulfuric acid solution with platinum electrodes, because you need a catalyst to make the reaction at room temperature. Okay. After that, they say if we decompose water, you get hydrogen, oxygen, and why we cannot do the reverse? So it means, can we do the combination of hydrogen, oxygen, and obtaining electricity in the reverse experiment? So they take one cell with hydrogen, oxygen, try to decompose water, doesn't work. So they put two cells, doesn't work. Finally, with 4 cells in series, they succeeded to decompose water. So this very important first reaction gives you the principle of electrolysis and fuel cells. Okay? We are discussing between us, between old professor, young student. So you can interrupt me when you like. We can discuss sometime. I am very flexible. Don't worry. You can say, what's that? Okay, I will try to explain. So now let's go to the. Oh, excuse me. I am so fast. Oh, come on. Yes, I have to again the beginning. If you go to the end, it's not normal to go so fast to the end. Okay, so another very key point that to understand this phenomena, we can draw such graph. So you will see many times similar graphs, but it is very important. You have here in the axis the electrode potential. I mean the individual electrode potential. It is not the cell voltage. You know, to make an electrochemical device, you must have 2 electrodes. With 1 electrode, you cannot do nothing. You cannot measure any potential, you cannot measure any current. So you need 2 electrodes. So for each electrode, I will show you, you can define an electrode potential. Okay, so in the axis, X, Y, or X-axis, you have the electrode potential versus a reference. Reference electrode, it's taken the hydrogen reversible electrode. I will show you a little bit later. And it is 0 by definition, which is wrong, because it is 0 at any temperature. But it is wrong, because we have temperature coefficient for elementary cell. And then you have in the y-axis the rate of reaction, the rate V. It is in fact the intrinsic rate, because it is the rate per unit square centimeter or square meter of interface. Because these electrochemical reactions are heterogeneous reactions, they occur at the interface between electronic conductor and the ionic conductor. The electronic conductor, as usual, metals, copper, gold, etc., electrodes, and the ionic conductor as the electrolyte with ions, protons, chloride, etc., etc. And the current density as a number of Faraday exchange in the elementary reaction times the intrinsic rate of reaction. So these 2 variables are very important. X-axis, that's intensive variable, intensive quantity in the sense of thermodynamics, and in the ordinate it is the extensive quantity, which is proportional to the number of mole to the mass of the reactant. And you see, you have 2 elementary reactions which are involved in the fuel cells. You have hydrogen and oxygen. With hydrogen, you can oxidize it, giving protons, or you can reduce the protons to give hydrogen. So it is reversible. It is nearly a straight line, vertical line, and you see that the deviation from the zero point, I mean zero current, which is more or less the standard electrode potential, is very small. This deviation is called overvoltage. We'll discuss that later. On the other side, you have the oxygen electrode, you have oxygen reduction giving water, oxidation of water giving oxygen, and this is quite different. At around zero current, you have a large domain range of electrode potential where there is nothing. So to make the reaction, we are obliged to go a little bit further than 1.23 volt, which is the standard electrode potential. In that direction, to evolve oxygen, that's electrolysis, from water, or that direction to reduce oxygen, that's the fuel cells. So you see this reaction, it is, we say it is not reversible, but it is a wrong word. It is not reversible. It means that you have overvoltage both directions to make the reaction. So the overvoltage means you have to add extra electrical energy to make the reaction. You deviate from the standard equilibrium potential. Okay? And in this figure, for the complete cell, you have to make the difference of, I would say, the anode or the cathode potential and anode potential, or anode potential and cathode, depending if you are fuel cells or electrolysis. For example, for the electrolysis, you must have the anode as here, this point, and the cathodic point as this one. So, by definition, anodic current is positive and cathodic current is negative. Anode means oxidation, cathode means reduction. So the difference between these 2 points, that's the cell voltage for electrolysis, which is 2.1 volt. That example. For the fuel cells, the cell voltage is the difference between the anode potential and the cathode potential in that point, which is positive. I mean, the potential is positive. That's the positive electrode. That's the negative electrode. But at the negative electrode, you have oxidation of hydrogen. At the positive, reduction of oxygen. The difference between the two electrode potential gives you the cell voltage for the fuel cells under working condition. So it's 0.7 volt. You follow me? No problem? I can stop a little bit? No? It's okay. So now, if you look at the practical efficiency, you have deviation from the standard electrode potential. So for the electrolysis, the efficiency will be the ratio between the standard 1.23 volt and the working cell voltage 2.1. So near 60% efficiency. For the fuel cells, you take the same ratio. I mean, the cell voltage versus the standard cell voltage, so it gives you 57%. If you think about hydrogen, oxygen, water systems, are storage of energy. I mean, you decompose water by solar, photovoltaic, etc. You store hydrogen, then you use it in the fuel cells. It's like a battery, like a secondary battery. The efficiency is very bad, very poor. So the overall efficiency is, you see the figure, 33%. So this explains why the Grove Schoenberg experiment, they need 4 elementary cells. With 4 elementary cells, they can have an efficiency of 25%. So it's okay. It works. So it is not possible. Okay. I am a little bit long, so I have to go. Bon. Okay, that's also a very important point, the difference between an electrochemical device and a thermal engine. For example, an internal combustion engine. You see, in this transparency, the most important point is the fuel cells or an electrochemical device like a battery is a direct transformation of the chemical energy into electrical energy. Electrical energy is a variation of the Gibbs energy minus delta G, giving electricity and giving heat. heat comes from the irreversible process, as discussed yesterday afternoon by Derek Baker. And for the electrochemical device, the efficiency is the ratio of the electrical energy versus the combustion energy at constant pressure minus the dBH, minus variation of enthalpy. So for any electrochemical device, you have a relatively excellent theoretical energy efficiency. For the thermal engine, the maximum efficiency is given by Carnot theorems, which is here, and which it is the difference between the heat of the hot source and in the cold source divided by the hot source. That's the mechanical work which is made compared to the heat of combustion, and you get this relationship, which gives theoretically between 30–45% depending on the temperature of the hot source and the cold source. The hot source is limited by the material and the cold source by your environment. And practically, you see, you have 18–30% for thermal engine, and for an electrochemical device, 40–60%. So roughly, an electrochemical power source gives you an efficiency about 2 times more than any thermal engine. That is theory. So that's the interest of electrochemical device. Another point here, it's how it works. For these 3 electrochemical power sources, elementary cell like electrochemical cell or battery or fuel cell, you have a box. In the electrochemical cell, in the box you have the chemical product, for example zinc and manganese dioxide, and they react, give you electricity. When it is finished, you throw away the box. Finished. With the battery, like lead acid battery, you have the possibility to make the reverse reaction, so it works in both directions. Oxidation of lead into PbO, reduction of PbO to lead, for example, and you can recharge your box of energy with electricity. So you can keep your device a long time. For example, in your car, you can keep for 5 years, 8 years if you have a good battery, lead acid battery. In the fuel cells, it's quite different. You have a box where there is a reaction, the electrochemical reaction, producing electricity and heat, and you have another box, a tank, with a fuel. So you separate the production of electricity from the storage of electricity. It is very important. In the battery, you cannot separate. In the same box, you have the storage of energy, you have the production of energy. So it means you cannot play too much with the size of the box or the volume, the mass of the box. But for fuel cells, both of them are separated. In the fuel cells, you produce electricity. In the tank, like in a car, in your car, you have a tank of fuel, you have the energy. And the energy gives you the time it will last. So for the car, the fuel cells can be comparable to internal combustion engine, where you have the combustion in your engine, and you have the storage of gasoline or diesel oil. So if you have a large tank, you can have long range, 1,000 kilometers. For the fuel cells, we try to have relatively long range between 400 and 600 kilometers. So it means that it is similar. If you can have a better storage of hydrogen, we can go further to 1,000 kilometers. You follow me? That's a very important point. Okay, I'm very long, each transparency. So just here you have a different kind of fuel cells. it was more or less shown yesterday. So you can classify the fuel cells with electrolyte, with a temperature, and with a fuel. Most of the fuel cells works with hydrogen and oxygen from air, but also you have some direct fuel cells using liquid fuels like methanol, ethanol, or hydrazine, or borohydride, etc. I don't go into detail. So, in fact, if you consider now the fuel cell systems, you have the elementary cell, which is again here. You have the electrolyte, for example, a proton exchange membrane, and you have 2 electrodes. So remember, for any electrochemical device, you must have 2 electrodes. Otherwise, it doesn't work. And the key point is you have separation of charge, like Ludwig yesterday told you, between the electronic conductor, which are the electrode, and the ionic conductor. It is very important to have a strict separation of charge. It means that hydrogen spontaneously is oxidized into proton and electron. The protons cannot go outside, and the electron cannot go inside this acid electrolyte. So they are obliged to be separated. Electrons are going out in the external circuit to the load, and protons are going inside the elementary cell through the electrolyte to the cathode. So proton plus oxygen as the cathode plus electron from the external circuit give you water. So you can explain, you separate both reaction, hydrogen oxidation, oxygen reduction, thanks to this device. And you have the overall reaction as production of water and of course of heat and electricity. But hydrogen is not a natural product. You have to produce it. There are many means to produce. We cannot discuss that. That's not the subject of this talk. But if you take a primary source like natural gas or like biomass, and you can make hydrogen with a fuel processor. Fuel processor means you have a different reactor like reforming reactor, like water gas shift reactor, etc., etc. It is not one reactor. It can be 3, 4, 5 reactor, and then you transform the primary source into a reformed gas, which contains hydrogen, carbon dioxide, carbon monoxide, nitrogen, and then you can feed the fuel cell stack. In fact, the fuel cell stack, it's a many elementary cell which are in series, which are coupled together with a bipolar plate to have the right cell voltage, total voltage, stack voltage. For example, if you take roughly 1 volt for the cell voltage, if you need 100 volt, you put 100 elementary cells in series. And the current is the same in all the elementary cells. And you have to control the fuel processor and the fuel cell stack. So it's a very complex system. An example of a stack by Ballard, it's an 80 kilowatt stack. So you know 80 kilowatts is relatively large. It's like in the car, in a sport car, maybe you have 100 kilowatts of the internal combustion engine. So you see all the elementary cells, they are in series, but there are 4 series of that. So to summarize, fuel cell systems, you see that the fuel cell stack where you produce electricity is a very small box, very small, and all around you have the auxiliary control equipment. So you have the hydrogen loop in red, means if you have a primary fuel, you must produce hydrogen, and because the fuel cells have usually nothing membrane, it needs humidification. It's water to be efficient. So you have humidification, then you feed the fuel cell stack, and you recycle hydrogen here with a pump. The oxygen loop as here in black, you take air from the atmosphere, it is polluted, so you must have filter, and you must feed the fuel cell stack with some extra pressure. You have a compressor, you have humidification, and you are preheating to have the working temperature of the stack about 70 degrees. If you take air from minus 20, for example, free start, you can begin free start, you have to heat the oxygen. Then oxygen goes out, but you have here for the PEM fuel cell, the production of water is at the cathode. So at the cathode you have a mixture of exhaust, water, and air, and so you have a condenser to separate water from air. And you have also to control the temperature, so you have a cooling process, changer, you have pump, then you have the load. Normally you have to adjust the voltage of the stack to the voltage of the load, so you have converter, AC, DC, 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 AC, DC, DC converter, and you have storage. If you don't use the fuel cells for, sometimes you need some energy to start, so you have a battery or supercapacitor to storage, for acceleration, and then you have a system control, which control the stoichiometry, the pressure, the hygrometry, the temperature, the cell voltage, etc. So it is a very, very complex system. The PEM fuel cells or any fuel cells, there is a lot of engineering, many engineering in many fields. So you have mechanical engineering, heat engineering, heat mass transfer, electrochemical engineering, chemical engineering. So it's very complex. So the thermodynamic data, just recall you that for the fuel cell reaction, the thermodynamic data must be negative because it is a spontaneous reaction and provide you energy with delta H and delta G. The cell voltage is a difference between the cathode, the positive electrode, and anode potential. And you must know how to calculate these for elementary reaction. So you see that the electrical energy is equal to the number of Faraday exchange times the cell voltage. Okay, it's here. And you can make reversible thermodynamics. That means the free energy on the reversible condition is equal to the external work. So you have two work. You have the electrical work and you have the mechanical work. Mechanical work is a product of pressure, which is supposed to be constant by the variation of volume. If you make all the good calculation, you arrive to this point that the electrical energy is equal to the variation of Gibbs energy. So the electricity comes from the variation of Gibbs energy. That's the main point. And Gibbs energy is the difference between enthalpy and entropy term. Okay. This law, if you look at the elementary law for any particles, you can write the variation of Gibbs energy in terms of variation of temperature, variation of pressure, and variation of number of mole of reactants, with mu E as a chemical potential. So when you introduce the chemical potential, you have the standard chemical potential plus RT logarithm of the activity of the species. The activity is more or less the concentration. It depends on the concentration of the species or the pressure. It's more or less the pressure. So this terms theoretically that's the activity. If you measure the cell voltage, you get the activity of the components. But practically, it is either the concentration in the liquid phase or pressure in the gaseous phase. And with this relation, you can define the potential scale and the Nernst law for half cell, that means for one electrode. By definition, for the reaction between proton and hydrogen, hydrogen plus electron, no, proton plus electron give hydrogen, that has a standard reversible potential for any couple, standard hydrogen electrode, and you take that zero, which is wrong, but it is arbitrary. You must have a reference point. But normally you make the difference between any electrode potential and this reference point, that you can calculate that by the Nernst law. I just don't want to make details the calculation. For any electrochemical reaction, I wrote any electrochemical reaction like that, A plus electron B. Why? Because usually you say ox plus an electron give red. But for some species, red and ox depends on the direction. For example, iron 2 can be oxidized to iron 3, can be reduced to iron metallic. So I prefer to have a general expression, A, that the species will react with electron, it means that the oxidized state, and B as a reduced state. And using this relation of chemical potential, you can derive the Nernst law. The Nernst law is very easy. You have the standard potential under standard state, which is related to the standard Gibbs variation, plus RT over NF, logarithm of the ratio of the activity, means of the concentration of the oxidized species versus the reduced species. So that's the general Nernst law, which applies at equilibrium. It means there is no current in the cell. It is complete equilibrium, and it is on the standard position. So I just recall standard position. It's 25 degree, pressure 1 bar, and activity of ion 1. That's the reference for, I would say, solution chemistry or solution electrochemistry. If you go to the gas phase, they have another definition. So it is not 25 degree, it is 0 degree as the reference point. And maybe the pressure is 1 atmosphere, not 1 bar, etc., etc. There are some subtlety about that. And then you have the scale. So by definition, standard hydrogen electrode is 0, and if you have positive electrode potential, it means you have oxidant. For example, oxygen is an oxidant. And if you have negative electrode potential, you have reducing species. For example, zinc 2 plus can be reduced. Zinc has the oxidized state, which is more negative than hydrogen. And for the extremity, you have the alkali, for example, sodium. Sodium gives you Na plus 1 electron, and the standard potential is minus 2.7 volt, whereas lithium, you have minus 3.1 volt. So you have a very large scale. Here you have the halogen, for example, or you have oxygen, of course, 1.23 volt, halogen, chloride, etc., 1.33 or 36 here, etc., etc. You have a very large scale. If you imagine, the scale could be 10 volt, minus 5 to plus 5. But if you have any solvent like water, water will be decomposed between 0 and 1.23 volt. So it means theoretically you can have very large potential window. Practically, it's not possible. This large potential windows means that you can do any reaction by electrochemistry. Any reaction which is not possible thermodynamically, I mean, in a closed reactor, you can do it by electrochemistry because you have the external energy. So you can decompose water, you can do anything with electrochemistry. is very powerful. Okay, so I just recall for the fuel cell reaction, hydrogen oxidation, oxygen reduction, and then you can calculate the electrode, the cell voltage, the difference of electrode potential at equilibrium. It is not on standard condition, it is at equilibrium. So you have the Nernst equation, and you have the pressure of hydrogen, partial pressure, square root of partial pressure of oxygen divided by the partial pressure of water. Usually, water is in excess, so the partial pressure is nearly total pressure, yearly. So one point is you can increase the cell voltage by increasing the pressure reactants, hydrogen, oxygen, and also you have the effect of temperature, which is contained mainly in the standard delta G0. Always a battery problem. Okay, so you see, if I have some here. Well, the temperature variation is contained in two terms. In the RT, R is a gas constant, and T is absolute temperature. But the most important variation is in delta G0, because you have the exponential term over RT. So you can make the calculation again. I don't do that, okay? And have the right figure. Cell voltage under standard condition 1.23 volt. Energy density 33 kWh per kilo. I also write the reaction in alkaline medium. In alkaline medium, you see that you have water production at the anode. For any anion, you have water production at the anode. And for cation, conducting electrolyte, it happens at the cathode. Now I will give you some important table. That's the thermodynamic data as function of temperature. Absolute temperature going to 1000 K. The variation of delta H, delta G. With delta G you can calculate the equilibrium or standard equilibrium potential, cell voltage, and you can calculate the efficiency. Okay. And liquid water is below 100 degrees, and then you have gaseous water. So the key point is, on the standard state, you have liquid water. And if you take the figure, which are again recorded as in a blue color, you get this very relatively high efficiency, 0.83. 83% efficiency. If you increase the temperature in the liquid state, you see that delta H is nearly constant and delta J, absolute value, is decreasing. So it means that the cell voltage is decreasing and the efficiency is decreasing. Okay? But if you are at the gaseous state, you see there is a difference in the enthalpy, a relatively large difference, about 45 kilojoule per mole, which is heat of condensation. In the gaseous state, you cannot use the heat of condensation, so you have the low heating value. In the liquid state, you have the high heating value. So it changed the figure, so it means it changed the cell voltage, it is lower, 1.16 for example. It changed the efficiency, which is higher, nearly 1 for, I would say, 300, 400 K. So that's very important. There is a jump of delta J, of delta H, of the cell voltage, and of efficiency from the liquid state to the gaseous state, as related to the heat of condensation. So normally, the efficiency is defined in the standard conditions, that maybe it is a wrong definition. It will be better to use the gaseous state, but it is not standard, because usually you produce water as a gaseous water in the cell, and then you have condensation, but you don't recover the energy of condensation. You follow me? It is more or less written here. In the liquid state, the energy change, heat of action, has a high heating value, HHV, which is equal to the low heating value plus the heat of condensation. And with the data I gave in the table before, you can calculate that the heat of condensation for water is 44 kilojoules per mole. In the gaseous state, you have this figure, and you have the low heating value as the heat of action, and if you take that as a reference point for the efficiency, you have higher efficiency. Okay? Is it clear for everybody? Yes?
For clarification, on the previous slide, you showed gaseous state at 298.
Yes. Let's suppose that you have a gaseous water at room temperature. But it is not true normally. It will depend on the pressure. If the pressure is 1, it is wrong. But it is just a point of comparison to see that there is a large difference at room temperature, 25 degrees, between the liquid state and the gaseous state in terms of enthalpy change and Gibbs energy change. The Gibbs energy change has a small change, but for enthalpy, you have large change due to the heat of condensation of water. And you can see also that in this graph, in this table, the enthalpy, delta H, is nearly constant. You see, from room temperature to 100 K, very small variation. So you can just think about delta H as constant, delta J, the absolute value decrease, so it means that the other term, T delta S, has increased with T. Okay? Okay, so again, calculation of under standard condition, the efficiency of the cell. Theoretical efficiency under standard condition means liquid water. You compare that to internal combustion engine working between hot source at 350 degrees Celsius and 80 degrees Celsius, you found 43%. So here again you have 2 times more energy efficiency for the fuel cells than for a thermal engine theoretically. This graph was more or less shown yesterday also. It is a comparison of the efficiency of the fuel cells and the Carnot efficiency. You can see because of delta J is decreasing, the fuel cell efficiency is decreasing nearly linearly. And the Carnot efficiency vary like a hyperbolic function over 1 over T. And for two cold source, one at 25 degree room temperature and the other at 80 degree Celsius, it means that the exhaust of a car, the exhaust of the car more or less 100 degrees. And what is the key point is at a relatively high temperature, both cars are crossing each other. It means that above this point or this point, the fuel cells efficiency is lower than that of internal combustion engine. So it means that for solid oxide fuel cells, we are not speaking about solid oxide, we are speaking about PEM fuel cells, low temperature fuel cells. But for high temperature fuel cells, the efficiency is lower than that of internal combustion engine. Okay? And for PEM fuel cells, which works between, I would say, ambient temperature and 80 degrees, you see the difference is very large. So when a big interest of PEM fuel cells, it works at relatively low temperature, it means that you have a very high efficiency, at least 2 times more than internal combustion efficiency. It is a key point. Why the development of PEM fuel cells are very important for our energy problems, energy crisis. If you have 2 times more efficiency, you use 2 times less fuel for the same energy, more or less. But now another point is the kinetics of the electrochemical reaction, because if you are working, the current deviates from zero, of course, you must produce energy, and I give you some elementary idea how you can deal with the kinetics. I said that in electrochemical reaction of the pipe, it has heterogeneous reaction. It means it happens at the interface between the electronic conductor, the electrode, and the ionic conductor, the electrolyte. And at the interface you have separation of charge and product. And because it is heterogeneous, you have mass transfer from the bulk of your system or your phase, mass transfer of the reactant to the electrode surface, and because for hydrogen and oxygen reaction, they must be catalyzed. It must be catalyzed by some tricky material which is called platinum. Platinum is the best catalyst for this reaction, room temperature or higher temperature. And in the catalytic process, we have a special process which is called adsorption. Adsorption means you have special interaction between the molecule and the electrode surface. The electrode surface is a catalyst. So you have preferential bonding between the reactant and the electrode surface. So you need at the electrode surface some free sites to make that bonding. If the sites are occupied by any poison, you will decrease the rate of reaction. This is important if you have pollutants in the atmosphere, or if you have CO produced by the reformate. CO is a strong poison of the platinum site. So the reaction occurs as an interface. At the interface you have exchange of n electron between A and B, then the product has to be dissolved, and then you go away by mass transfer. So it is a relatively complex reaction. So to analyze the kinetics, you can do that step by step, analyze any of these processes. Okay, for that we have to define the rate of reaction, which is the number of mole of A or B which are transformed by unit time, dNr over dNt, for example. And you can calculate the current intensity, that's the number of charge transfer by time unit. It's a number of Faraday. Faraday is at the charge of a mole of electron times the rate of reaction. So this important point, intensity is exactly the rate of the electrochemical reaction. And because the reaction is a surface reaction, we have to introduce the rate per unit surface area. So per unit square centimeter or square meter, so you divide by the surface area and you have the density of current, which is related to the intrinsic rate. Intrinsic rate means per surface area unity. And by definition, if you have a reduction, means gain of electron, the current or the current density or intensity
are negative. For an oxidation reaction, you lose electrons, you have positive current. That's definition. The definition is the same as you put electron negative and proton positive. You can do the reverse. You say protons are negative, electrons are positive. So it's convention. Okay, then you can calculate the current density for elementary reaction, assuming a first order reaction. In kinetics, first order reaction, the rate is proportional to the concentration. So it's written here, the rate, intrinsic rate, is a constant which depends on the intensive variable. Intensive means variable which doesn't depend on the quantity of matter, like potential, electrode potential, temperature, pressure, times the concentration, oh my god, excuse me, times the concentration. Okay? And you can use, you can use the Arrhenius law and replacing the rate constant K by some exponential factor of minus the energy of activation. This term, energy of activation. Alors, you have the star means it is activated state, the complex activated state, and tilde means it is a variable which depends on the electrical potential. It is called the electrochemical Gibbs energy. And this one can be written as a function of the chemical energy, Gibbs energy, minus or plus one fraction alpha of the electrical energy. Alpha is a fraction. It is called charge transfer coefficient. It is between 0 and 1. So you see that if you provide external energy with an electrical field, one fraction will activate the forward reaction with alpha, and one fraction, 1 minus alpha, will activate the reverse, the backward reaction. So that's the definition of alpha. And then you can make some manipulation. All the figures which are more or less constant are in K0 and in delta G0, and all that times NF, and the concentration in the bulk give you the exchange current density. The exchange current density is a very important variable for electrochemistry, and you see that you separate, in fact, the electrical part, exponential I alpha NF eta over RT, from the chemical part, which is here. And eta is a deviation from the working cell voltage or working potential from the equilibrium potential at zero current. So this is over voltage, which is another important point for electrochemical reaction. So you separate the contribution of the electrical part with eta and the contribution of the chemical part with G0. This is very important because in delta G0 you have delta G0 which will vary with the kind of catalyst. So the catalytic effect is contained in this delta G0. If you change of electrode, if you take rhodium, iridium, palladium instead of platinum, there is a change in this activation energy, chemical activation energy, change of G0, a change in the electrochemical characteristic. Okay, you follow me? And then you can write the overvoltage for activation reaction as proportional to logarithm of the ratio of the current density over G0 times RT over alpha NF. Now the other point is the limitation by mass transfer. The idea is the following. If you increase the current density, you increase the rate of reaction. So it means that you must have much more specials at the electrode surface to react. These specials are arriving at the electrode surface by diffusion as the first approach. So if the rate is increasing, the diffusion must increase. But at the limit, when all the specials arrive at the electrode surface, they are consumed. So the concentration at the electrode surface becomes zero. When it is zero, you have the maximum of current you can get from your system. Because you cannot go negatively. Zero, that's the minimum concentration at the electrode surface. The maximum concentration is when there is no current, that's the bulk concentration. Okay? So that's the idea. And then you can solve the Fick equation in the steady state. It's very simple solution. You see, you have the first law, the flux, density of flux is proportional to the concentration gradient times the diffusion coefficient. Okay? The current density is the same quantity times NF, and you have the second law, Fick law, which gives you the conservation of matter inside the systems, and under steady state, the variation with time is zero. So you can solve easily this equation, and you have between zero, the electrode surface, and a distance from the electrode delta, which is called the diffusion length, you reach the bulk concentration. So this approximation is linear, and you see that the gradient of concentration is the difference of concentration at this point and at the electrode surface. Okay? When the rate is increasing, this goes down to zero. You have zero concentration. The slope here is a gradient, so you have maximum gradient at zero concentration at the electrode. So that's the maximum limiting current density for transportation of the species.
But isn't that species gas?
It is equivalent, because in the gas diffusion electrode you have flow and you have the same concept. Permeation, of course, and if you reach the three-phase boundary, because in the gas diffusion electrode, in gas you have three-phase point where the reaction occurs. You must have protons, electrons, and oxygen, for example. And then high rate, okay, we can have the same concept. Okay,
Will you take a break?
we'll take a break.